A family gathering with presents and fun. Another Christmas and this one's wonderful. Presents and cheer, candy canes and gingerbread men.
But wait, the gingerbread men have come alive. They're moving round the room and now they're on fire. They're moving round the room and now they're on fire. Why do I see these things? It's not the rum and eggnog. It's not the holiday punch. It's Christmas on acid. Christmas on acid. My stocking's full of spiders and snakes. My little cousins have become walking, talking fruitcakes. The whole family's looking at me, 'cause I got the shakes. Why do I see these things? It's not the rum and eggnog. It's not the holiday punch. It's Christmas on acid. Christmas on acid. The turkey's dancing on Grandma's head, and her eyes are a devil red. Santa's dead, oh Santa's dead. Why do I see these things? It's not the rum and eggnog. It's not the holiday punch. Christmas on acid. Christmas on acid.
All right, so this is the last class that we'll have. Friday, of course, no class, but your last assignment out of 10 is due by midnight. First of all, I'll open it to any questions, homework or otherwise. No? All right. Well, in that case then, I've got a couple of old finals here that are going to have exercises somewhat similar to what's on your assignments. I don't know, maybe it will help to go through a couple of them. I don't know. For example, let A be a set of integers and let K be another integer. The sub-problem is, given this set and an integer K, does there exist a subset such that the sum of elements in S and that subset sums to K? This is, of course, NP complete. We go through this by designing a brute force style algorithm for this. So I guess if you were to design a brute force style algorithm for this, what kind of combinatorial objects would you be generating? Subsets, right? So if you wanted to, you could write out pseudocode that looks something like this, right? For each subset S of that set A. And I'll go ahead and repeat that it's elements A1, A2, dot, 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 AN, right? Right? What I'm going to do is I'm going to create, compute the sum, right, of elements S in S of S, right? And if the sum is equal to K, which is given as part of the input, then output yes. There does exist a subset of elements that sums to K. Right? Not that the subset is of size K, but the sum of elements in that is K. Right? So this is obviously going to be order what? If I generate subsets, it's going to be 2 to the n. Right? There's my brute force algorithm. Now, this is going to be order n, of course, but it doesn't really matter. Order n 2 to the n technically in total, right? But this is really the most important part right here. Okay. It is well known that this problem is NP complete. You do not need to give a full proof of this, but show that it is in NP by giving a non-deterministic polynomial time algorithm for it. So that one's almost just as much, virtually this, except that deterministically going through every single possible subset, you take care of this by using non-determinism. You guess a solution, right? So, 1, guess a subset S, and it doesn't have to be a particular size at all. You're just going to guess a subset of A, which again is A1 through AN. Right? And then 2, verify. Right? What you're going to do is you're going to compute the sum of all elements in that subset. Right? In fact, I shouldn't have used S so much. Let's go ahead and call them X in S of X. And if sum is equal to K, we're not going to output anything, right? We're going to accept. All right? Else, we're going to reject. That's what non-determinism was all about. Does there exist a computational path that leads you to an accepting state? If so, then you accept. You're able to magically do all of these guesses that you did in this deterministic version of it, you know, not order n, order 2 to the n, but instead order n non-deterministically, right? Non-determinism. This verification phase here, that's determinism, right? All it is order n to sum up all these elements and check to see if it's equal to k, and that's it. Right? The certificate phase is always deterministic. The guessing phase is where you do the magic. And literally it is magic because it is not a real computational model. It is a theoretical model. Right? See? Gomer's come up with a dynamic programming solution that does correctly solve the problem. So Gomer's right as far as his correctness is concerned. For this problem, it fills out a table of size n times k so that it has running time order nk. He rushes to publish his result claiming that P equals NP. Why is Gomer wrong? So where have we seen something like this that appears to be polynomial, but it's not? The 0, 1 knapsack, right? The 0, 1 knapsack, you ended up filling out this table, right? And I'll go ahead and adapt it here, where it's n by k, right? Or in the case of 0, 1 knapsack, it was W. But there's no restriction on K. There's no restriction on W, right? K, remember, is the sum. It's not bounded by n, the size of n. If it were, right, then of course this would be n squared, and so yeah, great, that's polynomial, right? But it doesn't have to be. K is an integer. There is no bound to it other than the input size. So if I gave you n bits, then k could be on the order of 2 to the n. Right? And so this entire thing right here could be of size 2 to the n. Right? K could be 2 to the n. Right? In which case you're filling out an exponentially large table, right? And defeats the purpose. You're right back at square one of generating every single possible subset, 2 to the n. In fact, that's exactly what you're doing with that table, right? N by a 2 to the n table. You're filling out every single possible solution. Okay? Design an algorithm that, given an undirected graph G equals V comma E, counts and outputs the number of connected components G has. Recall that the connected component of a set of vertices are all connected by some path. Give full pseudocode of your algorithm and a full analysis. Name your algorithm num components. Right? So how could we do that? Num components. Right? G. That's our algorithm. Right? My input is simply a graph. G equals V comma E. There we go. So one way that we could do this is here. I think I build on this later on. Right. Okay, no, yeah, we are going forward. I wouldn't have done it backwards, right? Okay, so how would I think you did this, right, as far as your programming solution. So how did you end up doing it? DFS, if you ever have to start over, count the number of times you have to start over, right? So I'll just put that as a high level here, right? Perform DFS, right? Each time you start over, increment a counter, right? Another way that you could have done it is simply by, well, for each pair, or run, or here's another one, right? Run Dijkstra's, or run either one, right? Run Dijkstra's or Floyd-Varshall. And that wouldn't give you the number of components, right? That would just tell you that there's this one vertex that's not connected to another vertex by another path. Yeah, that's not going to work. So the original solution here of doing a DFS, and every time you start over, increment a counter. This is going to be order n plus m for DFS. Okay? That was the idea there. And then we have you build on that. Design an algorithm that, given an undirected graph, determines if G is connected graph or not. All vertices are connected by some path, or a disconnected graph. Give full pseudocode for your algorithm and a full analysis. Name your algorithm is connected. So is connected, right, of G. Now, we intentionally gave that as the second question after that. Why? How could you use num components to solve this problem? Components of G. And if K is equal to 1, then output true, right? It's connected. Else, output false, right? So in other words, if we have a solution to this, then we have a solution to this. One of these reduces to the other, right? Is connected reduces in polynomial time to num components. Now, technically, again, this is a yes or no question. So this is a decision problem. This is technically a functional problem. Functional, right? We're not outputting yes or no. We're outputting a number, right? So how can you change it so that this is not a functional version? Instead, it's a decision version. What you do is you encode everything together. So G, comma, K. And this is going to be in the language or a yes instance if and only if G has K components. Right? And that's how you get around that technicality. Okay. Third one. Let G be an undirected connected graph. An edge is an edge cut if there's an edge, an edge E is a cut edge, is an edge that if you remove E from the graph, it becomes disconnected. Design an algorithm that, given an undirected graph G, determines if G has a cut edge or not. Give full pseudocode for your algorithm and a full analysis. So just to visualize this really quick, you could have like a connected component over here and a connected component over here, right? Maybe something like this. Now, this is going to be an edge cut, a cut edge, because if you remove it, right now there's one component. But if you remove this one edge, then there becomes two components. Right? Is this a cut edge right here? No, because removal of that still means that the rest of the graph is still connected. Right? Is that a cut edge? No. In fact, this is the only cut edge. So again, we're going to reuse the first two problems and solve this, right? Has cut edge of G, right? So for this one, we're going to do, this is technically a Turing reduction instead of a, but that's the idea that that's hidden in this. It's not a mapping reduction where you map yes instances to yes instances. A Turing reduction is where you're actually using a subroutine like we were doing right here. This is technically a Turing reduction because we are using the solution as a subroutine over here. Is connected. How could we use that? How could we do that? Right? So for each edge E in the edge set of G, right? So G is equal to V comma E. Right? So for each edge, what we're going to do is we're going to create a graph G prime, which is equal to V and then the original edge set and take out that edge. Right? In other words, we're going to cut it out. And then we ask the question, if G prime, or what was that, what did I call it, is connected, right? If not is connected of G prime, output yes. Now technically you would have to check to make sure that there was only one connected component to begin with, because if it's already disconnected and you're taking other things out, technically that's not a cut edge, right? So output no, right? It does not have a cut edge because cutting out any individual single edge does not disconnect the graph. Now you can also extend this to ask questions like, is there a cut edge set? So a set of edges that their removal will disconnect the graph. Now what's the minimum edge cut set, right? And that becomes hard or not hard. I forget off the top of my head. There's a vertex cut and then there's an edge cut and I forget which one is which. Right? Otherwise, the rest of this is just perform BFS, DFS, right? By hand. Don't want to do that, do you? No, I don't want to do it. Right? And I wrote it. This is kind of the opposite. If we wanted to do something like this, this is a thinking problem, right? So consider the set of vertices labeled A, B, C, D, E in a graph. Give an example of a graph whose with those vertices whose DFS discovery time would be A, D, B, E, C. Right? So what's the easiest answer you could give? A, D, what was it? B, E, C? B, E, C. Right. There, right? I didn't want it to be difficult. I just wanted it to be, if you knew how DFS works, you would immediately jump to this trivial solution, right? If you didn't know how DFS works, you'd have to sit there and think for a while, right? Give an example of a graph whose vertices whose BFS discovery to order time would be A, C, B, D, B, E. So A, C, D, B. I probably just made up these orders, right? A, C, D, B, E. So A, C, E, D, B. Just start out with the BFS tree, DFS tree, right? And there's your graph. Make no other edges. Give an example of a weighted graph whose vertices whose minimum spanning tree and the tree generated by Dijkstra's algorithm starting at A would be the same, right? So a weighted graph, hint, make it an unweighted graph by making all the edges 1, right? And then make it so that Dijkstra's algorithm would be the same as the minimum spanning tree. Well, guess what? Either one of those would work. Right? Yeah.
Question number 2, can't you also do what you did for number 1? Because that's all
Yeah, but you'd have to go a different order. A, C, E, D, B. Yeah. Oh, sorry. What, say for 2? Oh. Did I specify that? Oh, yes, I did. Okay, so I did make it a little bit non-trivial. All right, there we go. All right, so when started and using lexicographic order to determine which order to vert. Okay, good. All right, I didn't just make it terribly trivial. I'll keep that there so that we know what the order is. 1, 2, 3, 4, 5. Okay, so we want A and then C to preempt everything, and then E, D, B, your solution. That'd be work. Is it A, C, E, D, B? A, C, D, B. Oh, okay. Let me copy it down correctly then. A, C, D, B, E. There we go. All right, there. That's the correct one. Could we make something that's not trivial? Well, could I draw any future edge here at all? Nope. So I'd have to go with, otherwise BFS would have a different discovery. A, C, and then D, and then we could hang B off of this, and then hang E off of that. That would also work. Right. All right. Give an example of a weighted graph whose vertices, whose BFS tree would not be the same as created by Dijkstra's. There we go. So we can't use that one. Right. So Dijkstra's. There's my tree, and Dijkstra would want. Okay, so here we go. This is going to be. That's actually a good question. The BFS tree or the. Okay, yeah, this is the BFS tree, right? And then this is my special edge here. That Dijkstra would then prefer that if it were 1, and everything else is 2. There we go. Dijkstra would find the shortest path here to use this edge here, right? But the BFS tree going in lexicographic order would produce this one right here. Right, there we go. All right. Oh, there it is. Cut vertex. If give an example of a graph with 4 vertices that does not have a cut vertex. So taking out that one vertex disconnects the graph. Right? That does not have a cut vertex. K4. Say what? A square. A square would work too. All right. K4 as well. All right. So there's our example for A. Give an example of a graph with 4 vertices that has 1 cut vertex. So all you have to do is start it, like make it into a bottleneck or something, right? And I don't know. That's good enough. Or you could go ahead and add that. But you couldn't circumvent that 1 cut vertex by adding another edge. Right? The cut vertex, again, is right here. Design and analyze an efficient algorithm to determine if there is a cut vertex or not in a given graph G. So this right here, basically, but take out not an edge, take out a vertex. Right? So for each V in V. Right? That's it. All right. This is why I stopped writing exams because this is too easy. What am I? If you ask something too substantial on an exam, right? Then if it's too complex, then it's not reasonable to do it in like an hour or 2 hours or something like that. If you take that and then put it on an assignment, right? That's a little bit better because then it gives you time to think about it, right? Otherwise, it's just plug and chug stuff. Like the old one that I just looked at. Here's a graph, perform a DFS on it. Here's a graph, show me what Dijkstra's algorithm does on it, right? That's just plug and chug crap, right? And I don't like that. Design and analyze an algorithm that, given a weighted undirected graph, computes the maximum spanning tree of G. That's a good one. What would you do? Minimum spanning tree algorithms, and instead of, say, Prim's algorithm, instead of sorting them in ascending order, sort them in descending order, and so that you're always greedy and taking all the largest weighted one, right? Another idea here would be if you have an edge here with a weight W, transform it to 1 over W, and then find the minimum spanning tree. Right. Take the reciprocal weight. Now, if any of the weights are 0, of course, this doesn't work, but you can take those out and say, well, if it costs me 0, I'm definitely not going to take that in a maximum spanning tree, right? Unless I have to or something. Otherwise, I would definitely take that in a minimum spanning tree because it doesn't cost me anything. 0, 1 knapsack. Ooh, okay. Suppose that here's a corner case. Suppose all the values were uniform. Design and analyze an efficient algorithm to solve this problem. Hint, it should be no more than n log n. The strong hint there is that you're probably going to be sorting something. Does it make sense to sort it by the values? No, because they're all the same. So the only thing left to sort it by is the weights, right? And so how would you go about stealing stuff now? Yeah, least weighted, because so that you can carry the most stuff, right? Because all the values are the same, right? If there are stacks of $100 bills, does it matter that you take those $100 bills or those $100 bills? No, you take as many as you can, right? I guess you take the $100 bills, not the $100 coins or something. I don't know, right? $100 coins are usually like gold, so those would be more valuable or something. I don't know. The general 0, 1 knapsack problem is an optimization problem. We want to maximize our value subject to our weight constraint. Consider the following decision version of the problem. Given an instance of the knapsack K and a target value V, does there exist a subset whose elements sum to at least V? Suppose that you had access to an oracle, a free algorithm A. Did I put this on this homework? Yeah. Oh, okay. Skip it or not?
Well, not the exact thing.
Okay. Oh.
Like, it mentioned oracle. In the whole
Okay. It wasn't for 0, 1 knapsack though. I don't care if we do it or not. Given an instance of the decision problem, you gave a yes or no answer. So this magic algorithm here, given an instance of the knapsack and this target value here, it'll output yes or no. Design an algorithm to find the optimal value of the knapsack. Right? So the idea here is your knapsack is fixed. Okay, that's not going to change. What can change is your value, right? So A on this knapsack and say 5, if this is yes, then this means that there is a solution with value 5, right? If the answer is no, then there is no solution with value 5, okay? I want to find, yeah, because you're trying to find the maximum knapsack value, right? So we want to maximize V, where V is this other part over here, right? Okay, that's good. So let's go ahead and make this master value AB ABC QR X, say, is going to be the sum of all values VI. There we go. That's the maximum, like that. If you stole everything, that's the value of the solution, right? And so for k running from x down to say 0 would be, I mean, you can't take anything basically. Then if the algorithm given that knapsack, given k, is yes, stop and output k. Right? And that's it. Eventually you're going to get down to 0, which is a trivial solution, so you don't need to output anything down here at all. Right? There. It's efficient in that it is going to only be order x. Arguably that's not efficient because there is no bound on x. It could actually be 2 to the n, right? Like the sum of values could be exponential. So the idea here, I think that I screwed up on the way that I formulated this, because what you could do instead is let's change this so that a sub k, or I already used k, darn it, k, j. I should come back here and change this, j. There we go. Sorry. There's the knapsack problem, and v. And this is going to output yes if there is a feasible solution with value greater than or equal to v. Not exactly equal to v, but greater than or equal to v. Now what you could do? You could do a binary search. That x as before, you start at x divided by 2. And you say, all right, here is your range of feasible values, 0 up to x. So you start in the middle. Is there a solution that has value at least half that? No? Okay, well then search over here. Yes? Okay, well then, is there something with 3/4 that value? Right? Yes? Keep going higher, otherwise you've now cut it down over here. And if you're going from, say, 0 up to x, which could be 2 to the n, then your binary search is going to be on a domain of size 2 to the n, which is n, and now that's efficient. That's polynomial. Before, though, if you just had to go straight down, right, and this was 2 to the n, you kind of, you wouldn't be able to do it, right, efficiently. Right? Yeah. Yeah, and generally it is, because that's going to be n. But the weights here are only going to be bounded by 2 to the n, because you're allowed to have n bits. And what's the maximum value you can express with n bits? 2 to the n. So these weights could be exponential. This capacity could be exponential. It's not, only if it's bounded by a polynomial in n, then your pseudo polynomial time becomes real polynomial time, right? N times w. If w is order n, or order n to the k for some k, then the entire tableau becomes polynomially sized. So if you put that too much of a restriction on it, then it becomes solvable. Right? Yeah.
So the k is continuous. So if you have a k that's if for 1 k is yes, then for 2 k is yes.
Say again.
So like if there can be a value of 1 that's true. So like if there can be a value of 2 that's true, there can be a value of 1 that's true.
Not under this first formulation where it's exact, but under this formulation where it's at least as big, then yes.
Okay.
Right? If there's a solution that's at least as big, has a value of at least 5, right? Well, then there's also a solution that has a value of at least 2, right? Because maybe it was 7 or something, right? So that was the idea, and I don't think I did that well in summer 2021, right? The last time I did it in summer. Was it? Oh yeah, where does it say that? Yeah, that's the bonus there. But then the formulation wasn't correct enough, right? Oh no, at least there. I did do it correctly. At least V. There we go. Not exactly V. All right. Oh, good. I didn't screw up 2 summers ago. All right. I don't know. Maybe I did, and I fixed it and then handed it back out again. I seem to remember something like that. All right. I think that's. Do I have more? I think we did this one already. We did that one already. And yeah, and we've looked at this before. This goes back to optimal binary search trees, Dijkstra's, right? Draw an alternate BST. Yep. That's kind of what's on your. In fact, I think that might just be a copy of what's on your homework. So, yeah, go ahead.
The reduce columns, do we have to do the whole thing 5 steps?
If it says to, otherwise, it depends on which one are you talking about.
Let me see. Okay. When it says show that the number 3,
Okay.
show that the Hamiltonian cycle problem is incomplete by showing a reduction of Hamiltonian path. So do you have to do both the reduction and the mapping?
At least the mapping.
Okay.
I mean, it's kind of the other 5 steps are kind of trivial. Show that it's an NP. Well, guess, check, done. Show that your reduction is polynomial time. That's easy because you're adding a vertex and connecting it somehow, right? And adding a vertex is order 1 operation. Connecting it somehow to n other vertices is order n, right? So at least show and then argue why that's a reduction. Well, why would the original have a Hamiltonian cycle if and only if, or I guess from Hamiltonian path, that G has a Hamiltonian path if and only if G prime, where you've added this edge or this vertex and connected it somehow, has a Hamiltonian cycle. Right? The mapping is the important part there. Right. Yeah, good.
Also, a lot of them say reduction, and then one of them, 2 says design an algorithm. Do we have to analyze it?
Given to prove this, assume a free algorithm. So you're using this as a subroutine. So your analysis should state that a call to this subroutine is free. That's your elementary operation. How many calls do you make to this free algorithm, right? And your analysis should be with respect to that.
So we analyze it.
Yeah. I mean, it's not that big of a deal. It's how many times it's going to be in a for loop. How many times does that for loop execute? Order n, you're done, right? Let's look at. Yeah, go ahead. Not necessarily, but that's what you would check up front. If all of them were unset, then you ask your free algorithm, you get that out of the way up front. You ask your free algorithm, does there exist any truth values at all? And if no, then you can immediately quit, right? So now if the answer is yes, then okay, well now I go into another mode. Well, what if I set the first one to true? Does there still exist a solution? No? Okay, well, what if I set it to false? Does there exist a solution? Yes, right? So that tells me what that first bit should be, or what that first Boolean value should be. Yeah?
For 5 and 6, for 5, it says by showing a mapping, so you have to show that one maps to the other.
Yep.
So same thing.
Yeah, I mean, I would be formal about it just so that you don't go backwards. And I would do that 5-step process so that, you're not accidentally going, I mean, it's the same reduction, but in this case at least, but you're not going from the opposite problem to the opposite problem. Because that kind of gets into problems like this, right? Suppose that P1 and P2 are in NP and P2 is NP complete, right? Just look at that premise first of all, right? So here is NP. We'll go ahead and draw NP complete up here. and then P down here, right? And now P1 and P2 are in NP, so they're within this landscape, and that P2 is NP complete. Now, before we even look at the rest of the premises or the question, did I say where P1, P1? Did I say where it was in the premise? No, just that it's in NP. So it could be NP complete, it could be intermediate, it could be down here, right? We don't know any of that. Further suppose, though, however, that P1 reduces to P2. Can you conclude that P1 is NP complete or not? Provide a brief justification. So remember that it could be one of these three things. It could be here, it could be here, or it could be here. All we're told is that P1 reduces to P2. But we already knew that because that's the definition of NP complete, right? This is adding no more information than we already know. So does that necessarily mean that P1 is NP complete? Nope. It could be here, or it could be here. Right. So, a different premise. Say again? Yes. Because that means that it would reduce, and so therefore necessarily it would be up here. P1. Right? You know that it's in NP. Right? And having an NP complete problem reduced to it, by definition, that makes it, and transitivity, that makes it NP complete. And this one and this one have been ruled out. Now, does that so let's go ahead and start with the same premises, right? P1 and P2 are both in NP. And let's suppose that P2 is NP complete, and that P1 reduces to what did we say? P2 reduces to P1, right? Then this implies that P1 is also NP complete. Does it say anything about P versus NP? No, right? Now what if I were to change the premise so that I told you that it was right here instead? That P2 reduces to P1, and not only is P1 in NP, but also P1 is in P. Which one does that tell you? They're equal. Why? Because all you need is one NP complete problem to reduce down to a P problem, and that collapses the entire thing. Right? P becomes NP. Right? What would we need to do to separate them? It goes way beyond the scope of this course. You'd have to show that whatever proof you came up with, that there exists a problem that is not reducible to any polynomial time computable language. You'd have to overcome it was something called natural proofs. You'd have to overcome relativization, and I think like 5-10 years ago they came up with another third hurdle called the holographic algorithms. I don't even remember what it was. I've been out of the research area that long that I don't remember. Right?
You can't prove it's separate. You can't prove it's
Nobody knows how. And if you do claim one or the other, you've got some explaining to do. How did you do this? Because we came up with this bottleneck over here, this hurdle that even to begin to answer the P versus NP complete problem, or P versus NP problem, you have to answer this question over here, which seems to be an easier question, right? Because if you answer this question, only then can you look at this question, right? And so we've got 3 of those questions over here. How did you do that, right? And unless you address those, you know that crackpot, or they probably missed something. Right? Every few years, somebody will come up with a proof that's at least 50 pages, and so and it was written in LaTeX. And it was put on archive, only put on archive, but it's also somebody who's somewhat reputable, so maybe we should look into this. And they're not making these grandiose claims either. They're putting in, I think this might resolve the problem, but I'm not sure. Can you please take a look at my proof? Like they don't have the attitude of, I solved this problem, give me that money. they know that they've got a whole bunch of peer review to go through, the whole process to go through. Now, usually when that happens, it does become an interesting result because they've used some technique, or they've proved maybe something else that's not as strong but still of interest, theoretical interest or something. And so there is something salvageable usually out of those investigations, but only after other people have had their eyes on it and said, you forgot to carry the one. What's the other one here? Again, suppose that they're in NP and that P2 is NP complete. Further suppose that it reduces to P1. Can you conclude that P is equal to NP or not? That was just what I asked. No, you can't. You can't conclude either way. Right? That just shows that P1 is NP complete. Right? Now, if you added the fact that P1 is NP, then it would, of course, collapse everything. Right? Yeah, go ahead.
For number 6, it says integer between k between 2 and n.
Yep.
What is n?
N is what it takes a graph G. N is always the size of the vertex set.
Oh.
So this is with respect to graphs. If you ever have a graph G, V, comma, E, right? It's just standard to say that the size of the vertex set is N, the size of the set of the edge set is M.
So you didn't disagree?
Yeah, that's what you're supposed to do. Right? By convention, V is equal to V1, V2, V3, Vn. Okay. All right, well, again, make sure that you're filling out the course evaluation at some point. I haven't looked to see how many people have done so, but please do provide feedback. I have no idea if I'll be doing this course again next year. This is always, like the last 2 years, this has been on an overload. I don't know what I'm doing next year. So I think that there will probably be another H section. So if you've got a cohort coming up, tell them that the H is usually in the fall, regardless of who it is. Because we had actually 3 sections this year. I think. I don't know. I thought we started out with 3 sections. Everybody I've talked to has they said there's 3 sections. So I haven't found anybody that's taking that 3rd section at all. So maybe I'm wrong. Maybe they canceled it or something. But anyway, have a good break. And any questions, post to Piazza. Otherwise, I'll be grading your stuff on Saturday morning. Depends on volleyball, I guess. And otherwise, I'll wait for the volleyball game. No, wait. It's Thursday, Friday, isn't it? Okay, anyway. I'll get it done at some time over the weekend, and that'll be the end of the semester.